An insect zips through the air, buzzing fast and careless, when suddenly it collides with what looks like empty space. Only, it wasn't empty at all. The insect has struck a spiderweb, a net so thin it's nearly invisible, yet strong enough to halt the insect mid-flight. The fly's crash is the insect equivalent of a high-speed car hitting a wall, and the web still holds. As the web stretches and trembles, the spider senses vibrations traveling along the strands like signals down a wire. And that thread of silk wasn't even solid when it began. Inside the spider's body, silk doesn't exist as a thread at all. Instead, it's stored in liquid form, a concentrated protein gel, thick like egg white or syrup. Imagine a 3D printer hidden inside a blueberry. That's roughly the scale of what a spider carries in its abdomen, a fully functioning factory that can pump out one of the strongest fibers on Earth. Inside, the process begins with a shimmering liquid called silk dope. The name might sound like slang, but it's actually the technical term biologists use, the same name of the liquid polymers that get spun into nylon or Kevlar. In the spider's silk gland, this dope is a cocktail of proteins floating in water. It's not sticky yet, not solid, just a thick gel. But when the spider decides to spin, the dope travels through a long, narrow duct that works like a natural chemical refinery. Along the way, the environment shifts. The pH drops, water is squeezed out, and the proteins begin to line up. By the time the liquid reaches the spinnerets, the tiny nozzles at the spider's tip, it has transformed into a solid strand of silk. What humans do with pumps and high-energy machines, the spider pulls off inside a body no bigger than a coin. It's so efficient that scientists still haven't fully cracked how to replicate it. The spider turns liquid into thread seamlessly at room temperature without waste or toxic byproducts. A factory in miniature, run by instinct and evolution. No drying, no baking, no curing time. The spider creates finished silk at room temperature, faster than any lab in the world has ever managed. And not just one kind of silk. Different glands produce different versions, each with a purpose. The main ones are the dragline silk, the strong backbone threads that hold the web together, and the capture silk, sticky spirals coated with glue-like droplets. But there are many more. There's even safety silk, a lifeline the spider uses like a personal bungee cord, just in case it falls. The spider is, in effect, carrying a toolkit of liquid fibers, and with them it programs the architecture of its web. It decides which lines will be strong and taut, which will be sticky, which will be flexible. It's not just spinning, it's designing, and design matters. Some spiders build small, dense webs. Others construct huge circular ones, each species with its own blueprint. Even the same spider will alter its web depending on the situation. If it's hungry, it may build a bigger spiral to catch more prey. If it's windy, it reinforces the anchor lines. If it's disturbed, it may stop weaving altogether. NASA once tested this by giving spiders different drugs. A spider on caffeine produced a chaotic, messy web, like a child scribbles. On marijuana, the spiders seemed to lose interest halfway through, leaving half-built structures. On LSD, the webs were oddly symmetrical but incomplete. The results became famous as a quirky experiment. So what makes spider silk so special? In theory, it doesn't look extraordinary. It's made of proteins, just like your hair or fingernails. But inside the fiber, those proteins arrange in a unique way. Some sections crystallize, forming stiff regions that give the silk strength. Others remain more loosely arranged, creating stretchiness. This combination means spider silk can stretch like rubber, but resist breaking like Kevlar. By weight, spider silk is tougher than steel. A single strand can stop an insect moving at breakneck speed, absorbing, in a fraction of a second, an impact equivalent to several hundred times the spider's own weight. Imagine catching a bowling ball with a shoelace and having it hold. A silk thread can hold many times more load per gram than a steel wire of the same thickness. But the strength of a web isn't just in the silk itself, it's also in the design. Think of the radial lines as the spokes of a wheel, pulling everything tight toward the center. The spiral lines distribute force, letting vibrations spread through the structure. And then there's the most counterintuitive part, sacrificial failure. Some threads are built to break. When a fly collides with the web, the energy has to go somewhere. Instead of ripping the whole thing apart, certain strands snap on purpose. The damage is limited, easy to repair, and the rest of the net survives. It's strength by controlled weakness, a system designed not to resist everything, but to fail safely. Engineers call this a fail-safe. Spiders have been using it for hundreds of millions of years. Humans naturally took notice. Engineers studied webs to understand how lightweight structures can withstand huge stresses. Suspension bridges echo the principle of distributing tension across a network of lines. Earthquake-resistant buildings borrow the same idea of swaying without collapsing. In computer science, the internet itself behaves like a web. Data doesn't travel in one straight line. It moves across a network of paths. If one line breaks, the information finds another route. It's the same logic a spider uses when a thread snaps. The system adapts instead of collapsing. And in material science, spider silk is a holy grail. Imagine bulletproof clothing lighter than cotton, or surgical stitches that dissolve naturally inside the body. Labs have tried for decades to mass-produce it. Some have inserted spider genes into bacteria, yeast, even goats, hoping their milk might contain usable silk proteins. But progress is slow because spiders themselves refuse to cooperate. Unlike silkworms, they can't be farmed in large numbers because they tend to eat each other. So the spider remains the master weaver, far ahead of us. A spider's web isn't always meant to last. For orb-weaving spiders, the kind that build those beautiful, circular spirals in gardens, the web is disposable. Many of them spin at night, hunt through the dark hours, and then by dawn, they take it all down. Not because the wind blew it apart, but because the spider itself eats it. Yes, orb weavers recycle their own silk. Silk is pure protein, and producing it is costly. By eating the old web, the spider reclaims those nutrients and channels them back into its silk glands, ready to spin again. Watch an orb weaver at sunrise, and you may see the ritual. The spider walking slowly around the spiral, carefully plucking each line, until the entire net is gone. Often it leaves only the anchor threads, the strong drag lines tied to branches, so that nightfall brings an easier rebuild. But not all spiders do this. Cobweb spiders, the ones that leave messy tangles in corners, don't take their webs down. They patch them instead, which is why old cobwebs gather dust and hang in place for weeks or months. Other spiders also keep their structures, reinforcing and repairing them over time, rather than recycling them daily. For them, the web is a semi-permanent home as much as it is a hunting tool. A spiderweb is a living engineering system, spun from liquid, hardened by physics, perfected by evolution. Showing that real strength isn't about resisting every force, but about knowing where to bend, where to break, and how to begin again. Thank you for watching. If you want to help us weave the next story, give us a like.